Okay, so rolling contact bearings have these balls, right? Or rollers. So you got the outer race. So this is the outer race. And then you have the inner race. Sorry, there is a hole in the middle. Okay. Where's my eraser? Okay, so there is the inner race. This is the inner race. And then there is the outer race. And there is rolling elements in between, and they roll. Okay. Now, in contrast, bushings are plain, so it's very thin, and it's very compact. Okay, it has several advantages, as we will see. Okay, so clear all drawings. Now, this is an example here. There is a split. If you notice, there is this split here. The purpose of the split is for assembly. Okay, and it kind of acts like spring loaded, so that there is a hole, then you get in, and it's held itself in place. Okay, let's see what else they got here. Okay, here's some example cylindrical bearings with those holes. Sometimes they have graphite on it. I mentioned to you guys flange bearings. This is called the flange. Okay, I gotta turn on my annotation again. This is called the flange. Okay, so when you insert this bearing into a hole, and then it's stuck on it. Okay, so it's held in place with this flange, because otherwise, if you have a hole, you can go through and then it goes in too much, right? Here's an example of thrust washers. It's for axial loading. Remember, in bearings, right, you have radial, and then you have axial loading, right? This thrust is for axial. Okay, so what else are the examples? Okay, sliding plates. I mean, they're not round, but the principle of working is still the same, right? You need motion on a smooth surface. That's what bushings, bearings are all for, right? You have rotation with some loading. This is the same, I mean, but it's linear. Instead of rotation, you have linear motion on a load. The purpose then is to create a really nice, smooth surface. Okay, let's see what else this video got, right? You got all kind of different geometries there to contain lubricants many times, or you know, they do wear out too. Don't forget, these things, the material can be shaved off, and so where do the shavings go? These holes can also contain that. Now, there are several motion that is being mentioned here. Sliding. If you try to think of a, let me go into full screen here. Yeah. If you think of a shaft, you can have a plain bearing on the outside like this, right? And the motion then, the sliding motion is this way. It's like in the axial direction. Rotating motion is this way, right? Oscillating motion is a rotating motion that goes back and forth. So you can imagine oscillating goes back and forth like this. Clockwise, counterclockwise, clockwise, counterclockwise, right? Now reciprocating is basically a sliding motion, but back and forth. At other times, you might have a situation like in the internal combustion engine where you have a crankshaft, right? So this guy goes up and down, but the crankshaft goes this way, right? So if you think of this bushing over here, I mean, the motion is converting basically from linear to rotation. So the load is actually goes up and down also. It's a cyclic loading. Okay. Yeah, there are several other things being mentioned. Again, low friction, relatively low friction, not as low as ball bearings. High wear resistance, not bad. Bearings, if ball bearings, I should say, because these are also bearings, plain bearings. If you put a lot of impact load on it, it's gonna wear out quite fast. But these guys are much more impact resistance, shock loading resistance. Okay, you can imagine the bearings. Remember, they the ball bearings. I could say just bearings. Uh, these rolling elements, they create a point load. Okay, so the load at that point is pretty big. But these guys spread the load over a bigger area. In fact, that's one of the things that we will do in the calculation is this pressure, average pressure. Okay. But they are very good. Not good in high speed though. As you will see, there is a speed limitation. Okay. I will show you another contrast. Okay, go ahead and play this video. I'm gonna send it on the chat. Where's the chat? Okay, I'm sending another link in the chat. I'm gonna stop my share and go ahead and play the video. This is a comparison between metal bearings, ball bearings, and bushings. So we're gonna talk about some calculations here. There are several limits that we have to consider when we talk about bushings. Okay, first is the maximum load. This is the P limit. Okay, there is maximum temperature, but we'll talk about that later. First, we're going to consider maximum load, maximum speed, and maximum PV. Okay, so this is P, V, and PV. Now, if you think about P multiplied by V, it really is power, because P is related to force, and force is related, multiplied by velocity, is really instantaneous power. When you have friction, you have heat. This is the heat generated, measured by in terms of watt, basically, right? How much heat are you putting into the bearings due to this friction? I got some old annotations here. So you can pretty much, okay, how do I clear Clear annotations. How do we do that? Okay. These are some wear factors. It's kind of a measure of how fast it wears. Okay, that's K. You can see the oilless is basically a bronze bushing, these two. And then there are some plastic bushings. Okay, you can see the plastic bushings are quite significantly higher, K, meaning they wear out much, much faster than the bronze. Okay, you got nylon, you got some Teflon material here, Teflon with some glass. Okay, these probably some molybdenum. Okay, polycarbonate, sintered bronze. Okay, so this is the wear equation. Let's go straight to the okay, so you can see that bushings are basically pressured like this, right? It's under such pressure. What we worry about is the Pmax, because if the Pmax is too much, it's gonna create deformation that may not recover. So you have pressure and Pmax, okay, but this is what we worry about. V, velocity, and PV. Okay, you can take the average P multiplied by V here, or you can just do this formula. Okay, this is also okay. And notice that it is independent of D. Here's my wear equation. We're going to do that on the second problem. Here is some recommended design constraints. I'm having trouble deleting my old notes. Okay, I'll delete that. L over D, okay, if you think of a bushing, this is the diameter. Okay, D. I really should draw it on the other side. Okay, this is the diameter D, and this is the length L. Now, why do we have a recommendation of the length to diameter ratio? Well, think about it. You might have a bushing so short like this, or you might have a bushing so small and yet so long. Both are weird, right? So you don't want those awkward shapes. That's why we have an L over D ratio ranging from 0.5 to 2 in general. Okay, so you might have a length that is half of the diameter, or you might have a length that is twice. Well, that's not twice, obviously, that's much more, but more than the diameter. But let's stay within these recommendations. It's not, you know, like it's wrong if you go beyond that, but just a rule of thumb, right? Okay, any questions before we proceed to the calculations here?
Saya mau nanya, Pak.
Ya.
Itu nanti kalau yang L over D itu nanti pengaruh kemana ya, Pak?
Waktu kita select our bushings. So you don't want to, well, besides, usually the catalogs, the design catalogs will kind of constrain you there, right? The choices will be within those range. Jadi waktu kita nanti mau select our size, ya misalnya kamu udah select the D, when you select the length, ya try to be proportional gitu. Karena gini, kamu akan sadar bahwa that in design problems, there are always more solutions, more than one solutions, right? I mean, you can select this size or that size. Both are okay. Jadi waktu ada terlalu banyak pilihan, how do you reduce it to one solution? Well, sometimes you make assumptions, and I say, well, you know what? I can do a length of this, but I can do a length of this, but because of these recommendations, I'm just gonna find something where the size is kind of proportional. And that's also easier to find. If it's easier to find, it's usually cheaper. Okay, you will find that in industrial catalogs, the most common sizes will be cheaper. So it's not always that the bigger the size, the more expensive it is. The reality is, if they produce 1 million units instead of the other model that is only 1,000 units, the one that they produce 1,000 units will be much more expensive compared to the one that is, everybody uses. So common sizes, right? These kind of fall in that category. You want to select the common sizes so it's cheaper. Yeah, because there will be many solutions you can pick, but pick the one that is cheaper. Your boss will be happier and your salary will be better. Okay, any other questions?
Pak, mau nanya, Pak.
Ya.
Berarti kecepatan itu berpengaruh ke mana, bentar ya? Berpengaruh ke diameternya dong. Kalau misalnya kecepatannya naik, berarti diameternya juga meningkat.
Well, maksudnya begini. Kalau diameter kamu lebih besar, ya, notice this thing. Kalau diameter kamu lebih besar, velocity-nya lebih besar kan? Oke, kalau saya rotate shaft ini, dan kamu berdiri di tepi sini. Let's say you're standing on here, right? You're Ant-Man and you're standing on that rotating shaft. Now your speed going forward will be V equals omega R, correct? So the greater the R, the greater your V. So if you're standing on a bigger shaft, rotating at the same velocity, then angular velocity ya maksudnya ya, rotating at the same RPM, let's say this is 100 RPM, this is 100 RPM, you're standing on a bigger shaft, your speed will be bigger. Does that make sense?
Jelas, Pak, jelas.
Yeah, so when you choose your diameter and your length, you will have to take V or velocity into account. Any other question? Okay, so we'll proceed to this example. An oilless SP500, that's the type of the bushing. Okay, it's a brass bushing, alloy brass. 25 millimeter long, Celsius. We will start to get into temperature here also. The allowable wear without loss of function is 0.125, meaning that if this is my original bushing, there is this thickness, right? Now this thickness will reduce. It's gonna be, lubangnya lebih besar ya. It's saying that don't go beyond the amount of wear. If you go beyond that, the clearance between the shaft is too big, and you know, your vibration is gonna kick in, and it's not good. The radial load given. Okay, so at all times, this is applied a radial load, 2250 newtons. The shaft speed is given, is 200 RPM. Estimate the number of revolutions for radial wear to be 0.125. So here we're calculating the lifetime. Okay. All right, so let's jot down what we have here. So length, we're going to do everything in meters. Okay, I suggest you take a sheet of paper and write down as if you're in class. It just helps you focus. Okay, here my wear, this is W, not omega. The maximum wear is 0.125 millimeters, so (10 to the negative 3 meters. You have 200 RPM. I guess I should write N here instead of omega, because omega is usually given in radians per second. You got this force, radial force coming in, right? So again, this is your shaft going, you know, you have this pressure ongoing all the time, and the shaft is rotating. Okay, so that's the situation. We want to first evaluate the limits, whether the limits are reached, because if the limits are reached, then, you know, don't even talk about the wear. It's already violate the limits. So first, we have three types of limits. We have P max, we have V, and then we have PV. Okay, so P max, this is the formula. F is the radial force. High, 0.025 is the diameter. Length happens to be the same here. Okay, so if you look at it from the side, then the bushing is really square, right? Because the diameter is the same as the length here. Okay. We'll move some window here. Okay. Okay, so here we have the P is 4.58 MPa, megapascals. 1 Pascal is 1 Newton per meter square. Now velocity, pi dn. So pi times, this is really omega times r. You have to do n in terms of seconds. Okay, watch this. So we want RPS over here because our units, we want in terms of meters per second. So because I want my velocity to be in meters per second, then this n gotta be revolution per second. Okay, 200 RPM. Don't get yourself confused here. Okay, 200 RPM, 200 revolution per minute. it rotates 200 times per minute. So how many does it rotate per second? You divide by 60, right? So I go around the block 1,000 times in one day. I run for 24 hours, for example. I divide by 24 if I want per hour, right? So 200 revolution per minute, you want it in seconds, you divide by 60. Okay, now PV, you cannot just multiply 4.58 times 0.262 because remember in the formula, what we did was Pmax. We just did that, Pmax, okay? Pmax, not P. The average pressure is P. So when we say PV, it's the average pressure multiplied by V, not the Pmax multiplied by V. So we can just do the formula that is given. Therefore, again, N should be in RPS, revolutions per second. Length and diameters should be in meters. So we all do this on SI systems, yeah? RPM is not SI. Okay, so this unit is pretty weird. PV, which is in MPa, meters per second. Let me erase that. Okay, so here I have 10 to the 6. So that's really, the unit here is Newton per meter square, meters per second. And this is Pascal. So 10 to the 6 mega, 0.942 megapascal meters per second. Any question on the calculation? I want to now, I'm going to change color here a bit. Hold on. Let us compare that to the specifications of Euler's SP500. Okay, here's the specification sheet for SP500. The allowable Pmax, Vmax, and PV is given here. 24.5 MPa, 0.51 meters per second, 1.64 MPa meters per second. So we look at these calculations. I see that my Pmax 4.58 is less than 24.5 limit. So this guy is okay. V 0.262 is less than 0.51. Again, this is okay. This is less than 1.64 MPa meters per second, right? That's, make sure the units are the same when you compare it. They're okay. So meaning that the application that we have here right now will not fail the bushing immediately because it is still within the specification given. Any question on the limit evaluation? Next, we're gonna do wear evaluation. Ada ya? Okay, I'm gonna insert an empty slide here. Okay, now we're gonna do wear evaluation. Because we want to know when will it fail. And it does not fail because of violating the limits when it violates the wear limits. Now here we have the temperature. Sorry, not the temperature. This is the time. I want to show to you the original equation first. Okay, so here we have the original equation for wear on the bottom here. Okay, do you see my cursor? Yeah, di bawah ya. Wear is how much it wears out. Ya, kekikisnya seberapa banyak. F1, F2, I'll tell you about it. K is the wear coefficient. Pmax, Vt. Okay, so let me explain the formula first. Okay, we rewrite that here. The wear W is equal to F1, F2, K, what is it again? Pmax, Vt. Now Pmax you can substitute with, 4F, pi, dl, etc. Okay, but what I want to talk about here is first the concept of the formula, right? The wear is proportional to the K, which is the wear factor. Now I'm gonna ask you guys a question here. So if the wear factor is bigger, does that mean the bushing is softer or harder? What do you think?
Softer. Softer, Pak.
If the wear factor is higher, is it softer or harder? Anybody disagrees with softer?
Tapi kan tergantung sama pemakaian juga nggak sih, Pak?
Yes, that's T. Okay, but let's talk about the wear factor first. If wear factor is higher, then is it a harder or softer bushing? Any other opinion? Nggak ada. Pada tidur nih.
Lagi mikir.
Kalau K-nya naik, W-nya naik atau turun? Kalau
Naik, Pak. Naik, Pak.
W-nya naik, artinya kekikisnya makin banyak kan?
Iya.
Iya.
Kalau kekikisnya makin banyak, artinya dia lembek atau keras?
Lembek dong.
Lembek, betul. Okay, so wear factor is a material property, right? Look at this table at the beginning of the beginning here. Okay, you see the wear factor K. Let me change ink. These are all 10 to the negative 20. Jadi sama ya. Tinggal lihat angka depannya nih. Okay, you have these polymers, and then you have this oilless. Okay, ini brass ya, dari kuningan. This is less, so obviously kuningan lebih sulit terkikis, atau kebalikannya, polimer lebih lembek, ya kan? Dia kekikis lebih banyak karena K-nya lebih tinggi. Okay, so here the wear factor K, the higher it is, more it wears out. But obviously, as somebody brought up, it's not just the wear factor. This is kind of the material effect, right? And then you have how much pressure is it under? So again, the bushing, you have the shaft rotating, you have a radial load, which creates Pmax, right? The P kind of spread out here. The wear. V is the velocity. If you go faster, yes, kikisannya pasti lebih banyak dong. T is how much time you use it. Obviously, if you use it 24 hours, is more than 8 hours. Okay? Any question about the formula? So F1 and F2 are just modifying factors. You're going to start to see this in many of the formulas. Because again, machine design course here is a very practical course. You're going to see, you know, angka-angka yang mungkin asal-usulnya tuh lebih dari pengalaman di lapangan. Contoh di sini F1 dan F2. Oke. F1 itu adalah motion related factor. So, depending how much pressure and how much velocity, you're gonna have some modifying factor. Jadi ini mirip seperti kemarin stress concentration factor ya. Stress concentration factor, you know, is a factor that kind of increase the actual load. Mungkin loadnya 10 kilo, tapi atau 10 MPa, tapi it's made worse by stress concentration. Nah ini sama ya, F1 itu berusaha membuat kalkulasinya lebih konservatif. Jadi, okay, let's make it worse, gitu kan. F2 juga sama. Depends on the ambient temperature and foreign matter. Ambient temperature is the situation, right? If the situation has a higher operating temperature, then F2 is greater. Foreign matter juga, kalau ada debu atau dia suka kecipratan air atau whatever, right? Pokoknya pollutants gitu, dia tidak beroperasi dalam a relatively clean environment, then F2 is also going to make it worse. Okay, so that's the idea of this F1 and F2. All right, enough talking about the formula. Let's go into the calculation. Now remember, Pmax ini kan bisa disubstitute ya. Let me just give you the formula for T, time, that has everything substituted. So this is kind of the algebraic equivalent after you substitute everything. Okay, now we have to determine F1 and F2. Now F1 is determined based on P average and what was it? Velocity, yeah. Here, my P average. Did we calculate that? No, we didn't. Okay, so P average is F divided by DL. Again, there is a formula in the earlier slide. P average is 3.6. MPa. So here we fall in this category, 5 MPa or less. And then the velocity, we did that, 262. Okay, velocity is 262, 0.262 meters per second. Notice this guy is, this table is on millimeters, so it's 262 millimeters per second, right? So we fall into this category, and here's my F1, oops. 1,3 sampai 1,8. It is a range. I usually pick the worst. Engineers, we always do the worst. Okay? We are conservative. Unlike salespeople who thinks totally opposite from us. Some of you might become salespeople, by the way, which is fine. It's a good job. It's just a different way of thinking. Harus bermimpi dikit kan ya kalau sales ya. Engineers nggak boleh bermimpi, okay? Our priority is safety and that it works. Works the first times, works every time. Okay, that's our priority. Reliability. Now F2. All right, F2. It's not. Kayaknya kita dikasih tahu deh. What's the temperature? Clean environment. Okay. A clean environment at 21 degrees C. Clean means no foreign matter. Also means 60 or lower. F2 is 1. So we are not making it worse gitu ya. Kalau 1 ya kan anything multiplied by 1 makes no difference. So F2 is equal to 1. Clean and 21 degrees Celsius. Oke, tadi ini 262 sama berapa? 3,6 ya. That's F1 and F2. I think we have the rest. So we have 0.125. Oh, this guy W. W is, remember, is the wear limit. Yeah. Ini. The allowable wear without loss of function is 0.125. Okay. So you may not, the other way to look at this formula, right? What is the time to reach wear limit W? What is the time T to reach wear limit W? Right? That's what this formula is. So kita masukin wear limit 0.125 millimeters. So this is in meters. 4 dikali 1,8 kali 1. Okay, where do I get this from? 1207 10 to the minus 20. This is the K. And K is here. Wear factor is a material property. So the greater the number, the harder it is to wear, right? So K for oilless 500 is given. 1207. Here, the K is on the denominator for the formula T. T is the time to wear, right? So, ini kebalikan ya. If K is greater, then T is reduced. Jadi kalau dia makin keras, waktunya semakin rendah untuk mencapai wear limit. Sorry. Kalau K-nya for a greater K, ya kok terbalik ya? As K is greater, time itu reduce. I gotta think about that. The wear is increased as the time usage is higher, correct? Right? Kenapa?
Yang sekarang masalah wear coefficient kan masuk akal ya Pak, kalau dia di bawah.
Betul. Go ahead with your explanation.
Karena kalau dia wear coefficient kecil kan berarti dia lebih susah kegerus kan Pak. Otomatis waktu penggunaannya bisa lebih lama Pak.
Oh iya, sorry, saya terbalik tadi saya ngomong ya. Kalau wear coefficient lebih kecil, dia lebih keras kan, bukan lebih soft. Sorry, saya yang terbalik pantesan. Oke,
Iya,
so
Pak.
right, thank you. So wear coefficient-nya lebih kecil, artinya kan dia lebih keras. Makanya time-nya lebih lama. Yap, sorry for the confusion here. Okay, so K is 1207. Okay, it's looked up in a table. Yang tadi jelas ya, kalau ada yang masih bingung gara-gara saya terbalik, let me know. Okay, so 1207, the force in RPS, remember, the N, always in seconds, jangan lupa ya. In seconds. Okay, so now we find this is 4.79, 10 to the 6 seconds. Because we do everything in SI and in seconds, then our result will be in seconds. That is equivalent to about 1331 hours. I wonder what that is in terms of days. Anybody want to calculate? 1331 dibagi 8 jam operation. Berapa hari itu? The problem asks us to calculate the number of time.
141.
141 hari ya?
Iya, ada 0,3 Pak, cuman ya udahlah.
Right. 141 hari for 8 hours operation. Well, that's pretty fast. Cuman ya artinya harus dijadwalin kan? Maintenance. If you're an engineer, you do these things, one of them is for preventive maintenance. Jangan tunggu rusak baru diganti. That's Indonesian style engineering. Kalau proper professional engineering, you replace it before it fails. Itu namanya preventive maintenance. Karena begitu it fails, machine downtime, mungkin barang-barang kamu ada yang rusak, produksi, maksudnya produknya ya, misalnya kamu punya mesin memproduksi, stickers atau whatever lah, papers gitu ya, because your bushing is out of spec, everything messed up, produk kamu defect, kebuang. Jadi ganti sebelum failure, jangan setelah failure, jangan nunggu rusak baru diganti. It's one of the best practice of engineering, ya. Number of revolution is 200 RPM dikali 60 dikali 1331, karena ini jadi menit ya. Ini saya balik deh. Dan 200 RPM. 1331 jam, hours, mesti dikali 60 menit per jam. Or you can just do seconds, 200 divided by 60 kali ini sama aja. Okay? About 16 million revolution. Okay. Any questions on this problem? Yang pertama, kita limit evaluation, make sure everything is okay. And then we do the where evaluation. Ya, ada yang ngomong tadi?
Pak, tadi tuh where-nya itu di assume ya? Atau ngambil dari table ya?
Oke, ini where-nya where limit ya. Jadi bukan where coefficient yang 1207 kan? Kamu nanya yang 0,125 ya?
Bukan, itu yang where yang kita pakai sekarang.
Which number?
Yang 0,125, Pak.
Ya, yang 0,125 itu berasal dari limitnya. The allowable wear without loss of function. Jadi artinya terkikisnya hanya boleh 0,125.
Oh.
Ya. Jadi
Ya.
ini limitnya. Kita sedang calculate how much time does it take to reach that limit. Yeah, so this formula says what is the time t to reach where limit w, which is 0,125 milli.
Oke, Pak.
Yeah. Any other question? Okay. Let's take a break there before we do the second question. This one. 12.8. Now this one is a design problem, meaning that you are about to select a size. Kalau tadi kan size-nya udah dikasih, we are doing what is called analysis, right? But when we in the real world, oftentimes you're given a situation and you're about to select a component, a design a component, right? Here we are going to select from a catalog. So first we need to look into the design equations and select the length and the diameter. And then there will be some iterations that we will have to do because again, there are more solutions than one. Let's jot down our design requirements first here. We have an oilless 500 bushing. Okay, you're given the material types, so you don't have to pick the material type. There might be other problems where you have to you might need to select a material type. Okay, the maximum wear is given 800 hours operation. That's the time. 5 revolutions per second. Journal means the shaft, yeah. Jadi the shaft that rotates is often called a journal. Journal is the surface it rubs on. Okay, 220 radial load, that's the force. You're given some additional coefficient there. We'll talk about it. That has to do with the temperature effect of the bushing. Okay, Tmax is given. Fs is the friction coefficient. Design factor is given. Now, design factor is like safety factor. So the way you will use this design factor is simply multiplying the load with a factor of 2, just like stress concentration or other applications where we have an increased margin of safety. right? That's what design factor is. We are given the list of available bushing. Here, the dots, the dots represent the available ones. ID is inner diameter, OD is outer diameter. We will use ID as the diameter in the formula because the interface between the shaft and the bushing is on the inner diameter. Okay, the outer diameter is just
Ada yang mau join, Pak?
Oke, itu ada di mana ya? Karena ini saya agak salah sih, saya pakai sistem meeting room. Nggak ada, ini udah semua. Maksudnya ada yang di waiting room maksudnya?
Katanya sih gitu, Pak. Nggak connect-connect katanya, Pak. Cuma nggak tahu, Pak. Kayak kata internetnya, Pak.
Iya, I don't see any okay. Yeah. Yeah, I disabled the waiting room already. So if anyone enters, they will enter.
Oke, Pak.
Okay. So these are the list. This is a table showing you the available bushings that is available from the supplier, right? All these dots then are combinations. So for example, this is the length on the top, right? So for diameter, say 16, diameter 16 millimeter, you have a bushing with a length of 16, right? 20, 25, 38. That's what it means. Okay, so all these dots represent the available bushings, which is typical of the real world. You know, you basically are limited to in your options. You cannot just select any size you want. So back to the problem, we're going to have two criteria when we select the design of our bushings. We have wear, okay, wear criteria, and then we will have temperature criteria. You ask yourself, well, what about the Pmax V and PV that we calculate in the previous problem? Well, that is something that we will ensure that our size meets those criteria because they really act as limits, right? As long as you don't violate that limit, you're fine. But these wear criteria and temperature criteria will determine your size. Those, they kind of like an after check, okay? You check it after you select the size. So with wear criteria, we're going to use the formula related to wear. Now I'm going to give you the formula that is already rearranged for the algebraic solution L. Okay, the length is already given on the left side of the equation. It's still the same formula. Okay, F1 and F2, you understand from the previous problem. K is the material property. The F, the radial load, is multiplied by ND, the design factor, as I explained before. We're going to multiply it by 2 to make it worse than the reality for safety factor. N is the RPM, but in seconds. Good thing we already have it in revolution per second this time. T is the time. Okay, we're given 800 hours here. Okay, so the problem we ran into now, how do I select my F1 and F2? Because I do not have my pressure and velocity yet, right? Remember, we selected F1 and F2 based on the characteristic pressure and the velocity. Well, we don't have that yet. You cannot calculate pressure without the dimensions. And you have the velocity, but you don't have the pressure, so I cannot select my F1. What I'm going to do then is I'm going to put 1 as my F1 and 1 also for my F2. So just put it in. We're going to iterate and make sure that it still fulfills the requirement. Okay, so 1 and 1. Still same guy here, Euler's 500. So K is 1207, 10 to the negative 20. Design factor is 2. Load is 220. 5 revolutions per second. 800 hours in seconds multiplied by 3,600. The wear limit this time is 0.025, 10 to the negative 3. We solved that this is 12.2 millimeters. Now, this is where it takes a little bit of imagination. Here, the length that we solved is 12.2 millimeters. What is this length? Well, this is the critical length at which you will wear out 0.025 in 800 hours with this load and this velocity, right? So if you have a bushing with a length of 12.2 millimeters, then you will wear out 0.025 millimeters in 800 hours. That's what it means. Now, let me ask you this. Do you want your length, is this a minimum requirement or is this a maximum requirement? In other words, does my length has to be less than 12.2 or does it have to be greater than 12.2? It's an open question.
Greater.
Okay, somebody says greater. What about the others? Anybody says it has to be less than 12.2? Any other opinion? Why does it have to be greater? What's the explanation?
I think it's clearly can be seen from the equation. If you put a higher L, assuming the N and the and everything else is the same, the maximum wear will be less than 0.025.
Okay. So doing the same logic, actually, you can also manipulate the wear, right? The wear W. If I want less wear, my length has to be higher. If I want more wear, length has to be less. Obviously, we want less wear or higher wear.
Less.
Kita mau kekikisnya banyak atau dikit? Tentu aja kita mau sedikit. Kalau kekikisnya sedikit, lifetime-nya akan lebih lama, gitu kan? Atau dia bisa tahan load yang lebih besar. Jadi artinya kita mau length kita actually, oops, let me go back to so because we want wear to be minimal, then length has to be maximal in quotes. Okay, so length has to be greater than equal greater than or equal to 12.2 millimeters. Okay, this 12.2 is critical length. It doesn't mean we want it 12.2, because if we have it to 12.2, it will be risky sekali gitu kan. The second one is temp criteria. Okay, so that's where criteria. Here is temp criteria. So again, I will already rearrange the formula. Okay, this is the temperature increase. Okay, delta T is the temperature increase, and we are given the limit of 149. So again, this is the critical length. 0.03 is the friction coefficient. We multiply the load by 2, 5 revolution per second. 13.3 is the HCR, which is the heat transfer coefficient. And delta T is the temperature increase. It is the delta from the ambient temperature. Obviously, ambient temperature in Indonesia is not 20, but it's a common ambient temperature to use. So in the textbook, it uses 20. I don't think we're given here in the problem what the ambient temperature is. Everybody understand ambient, right? Ambient means like the environment, the environment temperature. So we may not exceed 149 degrees Celsius. So this criteria will give you the critical length, 38.4 millimeters. HCR is the heat transfer, because this is talking about the temperature increase of the bushing as it's being used. Okay. Same question. Do I want my length to be less than 38.4 or to be greater than 38.4? Anybody wants to answer? Yeah, Michael.
Can you repeat the question, sir?
So same question as the where criteria. Do I want my length to be greater or to be less?
Kayak kalau dari temperature sih lebih enakan less sih, Pak.
Kenapa?
Kalau kayak pembuatan besi gitu, kalau setahu saya kalau lebih panjang dia kemungkinan lebih ngeband ya, Pak. Kalau misal dia makin dingin.
Kalau lebih panjang, lebih mungkin bending. Okay,
Yeah.
but this is not talking about manufacturing, right? This is talking about usage. So under use, while the bushing is being used, the friction will develop where? Will develop temperature increase, develop heat.
I think it should be greater again.
And explain.
Because in the equation, the delta T is in the lower part. So if the temperature is not 149, of course the L will be increased.
Right. So if you want to operate colder, right?
Yes, you should increase the L.
Yes. So if the denominator goes down, L goes
Will
large.
be rise.
So the relationship is an inverse relationship. If you want it colder, then you have a longer bushing. Shorter bushing, you will develop heat more, which is kind of makes sense if you think about it, right? You know, with greater mass, greater surface area, temperature will be spread out more, and you can just take more heat, right? You can operate colder.
Yes.
So you want L to be greater than or equal to 38.4 millimeters. Both of these, again, you want a longer L, turns out. Which again makes sense with wear also, right? The greater your length, then the greater surface area, less pressure, kikisannya juga pasti lebih nggak gampang habis. Kalau kamu lebih tipis, lebih cepat habis. Makes sense. If both of these has to be greater than 12.2 and greater than 38.4, then obviously this criteria then rules, right? So basically, here we want delta T to be down, right? You want it colder. If smaller delta T is better, then greater length is better, gitu kan? So this is the determining criteria. If this is the determining criteria, then we are going to choose our L from this table. So now my L gotta be greater than 38.4. I wouldn't choose 38, I guess. I'm gonna go with 44. Can I use 50? Sure, right? There is no one right answer in the back of the book. It's kind of different than simple math or arithmetic. There's only one answer. In design problem, there are multiple answers possible. So greater than 38. So we're left with 44 and above. Let's choose 44. Gonna need an additional slide here. Okay, we're gonna choose length equals 44. Remember, there is a general design guideline. Who remembers the guideline?
L over D between 0.5 to 2.
Right. So we don't want it too long and small or vice versa.
Pak, D-nya itu outer atau inner Pak yang dipakai Pak?
Kita pakai inner. Tadi saya sempat jelasin. Anybody wants to re-explain that? Why do we use inner? Ada yang ingat nggak? Kenapa ini ID-nya yang kita bilang diameternya, bukan OD? Ada yang ingat? Kalau ini bushing, kalau ini bushingnya, surface yang bergesekan dengan shaft yang mana?
Inner.
Yep.
Oh, oke Pak.
Yeah, so that's where the interaction happens. That's when the heat develops. That's where the wear happens. So it's all about the ID, not the OD. The OD is just to, tell you the thickness, and also it fits in a housing or in a hub with certainty. Okay, so if I take L over D equals 0.5, then that gives me a lower boundary of 22, right? Di sini kan batasnya L over D is 0.5. Kalau L over D is 2, then that's like way down here. Oh, sorry. L over D 2. D is L over D. D-nya jadi setengahnya kan ya? Ini setengahnya kan? That's L over D equals to 2. Sorry, bukan 0,5. Di sini kan L over D equals 2. Kalau L over D equals 0.5, then it's twice. So it's all the way here at 88, right? That's L over D equals 0.5. So you see that all these dots kind of follows that guideline. But, let's not be oversized or over designed. So let's stick with D equals 25 or 30. Think about the formulas. Remember the formulas. Remember, we have 3 criteria. Look at these formulas. Just generally speaking, is small d better or high D better? Anybody has an opinion? If these are my limits and I want to make sure I am under the limit, do I want small diameter or large diameter?
Depends, Pak. If you
Yeah, it's not as
not as easy as it is.
straightforward. Karena kalau D-nya kecil,
We can get good V.
ya
Tapi
velocity
P-nya besar.
P-nya besar. Kalau D-nya kebesaran, V-nya nanti mentok. So, unfortunately, we have to do some iteration, or in other words, trial and error. All right. So let's start with L. L was 44, right? And let's use D equals 25. P max 4 over pi F over DL, but don't forget we have a design factor, so I'm going to insert it there. 4 over pi 2 times 220. Here's my D, here's my L. Okay, I end up with 0.51 MPa as a Pmax. This is less than my limit. Way less. So I'm okay. Let's check our V. No design factor here. It's just a geometrical calculation. It has nothing to do with forces. Velocity is simply kinematics. 0.39. Yes, it's less. Awesome. One more check. PV. Again, I have my ND multiplied by F. Dikali, I'm doing something else here.
Kayak tadi di PV nggak ada D-nya deh, Pak.
Iya, tapi itu ini soalnya. There are two ways of calculating PV, right? We can do this, pi Fn over L, atau ambil ini, dimultiply sama ini, which it cancels. Tadi apa? P apa? In my head, in my notes, I did it differently. So let's just. F dibagi apa tadi? Where is my other notes? Oh, pi Fn over L. So we have the ND here. 2 times 220 times 5 over kamu juga bisa P average, you calculate P average multiplied by 0.39. That's how I did it on my old notes. Okay. 0.156 should be the same. And this is less than 1.64. Good news. We passed all 3 limits. Okay. So the answer is yes, we can use a D is 25, L is 44. If you want to do a check using just for fun, okay, check D equals 30. Let's say D equals 30, then P max and PV will be okay. We don't have to check. Why? Why? Well, we don't have to check if D is increased because if I increase D, P max is smaller. So no worries, right? Same here with PV because PV actually is independent of D. But here we're just doing just a check, right? Okay, we don't have to redo P max and PV. Let's check V. Getting close, but it's still less than the limit. So it's also okay. So let's say in the real world, you do this calculation and turns out that a D of 25 and a D of 30 also both actually work. So how do you decide which one you want to do? How would you select your bushing? Dua-duanya oke.
Yang lebih kecil
Kenapa?
lebih murah.
Mungkin, belum tentu. Ya, apalagi faktor-faktor dunia nyata yang mungkin memengaruhi selain
Lifetime ya, Pak.
Oke.
Dari lifetime mungkin, Pak.
Let's look at our lifetime calculation. Where is dependent on length, not really dependent on diameter. Same here with temperature. So maybe not a big deal in terms of wear and temperature. What else? Think of a real world scenario.
Dari lingkungannya, Pak, mungkin, Pak.
Dari apanya?
Lingkungannya, Pak.
Lingkungannya gimana tuh?
Ya, misalnya dipakai di lingkungan yang banyak partikel-partikel gitu, Pak. Apa sih namanya? Kayak kotoran-kotoran kecil gitu, Pak. Jadi pas lagi beroperasi, dia ada debu-debu dikit masuk gitu, Pak.
Tapi kan itu tidak mempengaruhi diameter. Harga tentu aja menjadi faktor. Atau
Itu, Pak. Housing ya, Pak.
Oke, the housing mungkin punya housing chef tertentu yang sudah ada preference lain. Jadi kadang-kadang jangan lupa ya, ini kan kita calculate buat satu komponen, the bushing. But what about the shaft itself, right? Maybe the shaft needs to be a certain size, which then drives your diameter. Atau mungkin di gudang udah ada. Jadi bos kamu bilang, wah ngapain kamu pakai yang 25, pakai yang 30 aja, kita udah ada di gudang, gitu kan. Kita udah ada ready stock. Atau mungkin shaft di sebelahnya ukuran segitu. Ya kamu jangan bikin shaft kamu beda. nanti kita mesti stok spare part dua size, mendingan size sama, sehingga kita beli spare-nya satu aja, bisa dipakai di mesin sebelah, bisa dipakai di mesin kamu. Nah, ini kan aspek-aspek yang mungkin non teknis tapi mempengaruhi keputusan teknis. As long as it remains okay in your criteria check, gitu ya. So just kind of give you a perspective yang mungkin agak berbeda. Okay, don't forget we made an assumption. We're not done. We made an assumption. F1 and F2 we assume to be 1. Right? It is not 1 in actuality. So we have to recheck with F1 and F2. F2 is environment dependent. So actually in this case, we're not too worried about that. F2 remains 1 because the working environment is not hot, no foreign matter. But F1 falls here. If I calculate the average pressure, let's see, the average pressure will be, ada yang bisa calculate? Pakai kalkulator ya. Tadi kita pilih yang mana? Kita pilih yang 025 aja ya. Ada yang bisa hitung? Berapa average pressure ya?
ribu Pak. 400.000 Pascal.
0,4 mega.
Ya,
0,4 MPa. Which makes sense, right? Because our Pmax was 0.51. Ya, di sini juga ada ketahuan sih sebenarnya. Pasti 5 or less ya, kategori ini. Velocity-nya di sini, ya kan, kita berapa tadi? 0,39 ya. 390 mm per second. So our F1 ranges from 1.3 to 1.8. I like to be conservative and just check for 1.8. Okay, if we check with 1.8, you can do an L check, right? The length, remember the length criteria we did? Ini. Kita masukin ulang dengan F1, F2 yang baru. Atau kita juga bisa do a wear check. Okay? For the sake of change, kita latihan aja. Kita pakai wear check ya. Formula for wear. If I put in F1 equals 1.8 and put in everything else, I obtain that the wear is this much. Okay, which is less than 0.025. Remember, this is the wear limit. So this is okay. This is saying that my wear will be 0.0125 with the selection L 0.044. Okay? Under F1 as the worst case scenario 1.8. So my wear is still within the acceptable limits. Tadi ada yang nambah annotation ya, yang kuning itu. Kamu mau nanya atau gimana? You have a question? Okay.
Nggak ada, Pak.
Yeah. So that's the calculation. That's the design selection, right? First, we consider wear criteria and temperature criteria. We are actually determining length. We're determining length because wear criteria and temperature criteria only affects length. We see our length. There are several options for diameter, and we choose 25 or 30. Both works. If you selected 38, then most likely you will violate the velocity criteria. We check everything is okay. We put in F1 equals 1.8 again, and it's still okay. So we have our solution. Any questions? Again, in the quiz, all formula will be given, and you can end up with a different right solution. It's okay, right? There is no one answer key. You can interpolate if you want. I just use the worst one. A bit lazy. I'm gonna give you guys this one as the homework, I think. Problem 12-23. I'm gonna talk about one last thing about plane bearings. Okay. So plane bearings are like this, right? But they do not have lubricants as a, as a flowing liquid. Okay, these things, they are kind of dry, actually. Whether it's plastic or bronze, they are dry. But there is one more plane bearing type. It's called the hydrodynamic bearing. Now, a hydrodynamic bearing has fluid as the supporting lubrication. In fact, the shaft actually floats inside a hydrodynamic bearing, also called journal bearing. Okay, these are the bearings. You see this little hole? I don't know whether it's too small in your screen. This little hole is where the oil actually is being pumped into it. It can be a grease. Many times it's a bearing though. Okay. So this shaft is actually immersed. There is an oil flowing between the shaft and the plane bearing. This is what you have in your car. Okay. Trying to find a good, nice animation of the here. Saya coba ya share. Ini kan screen sharing kan ya? Saya coba play di sini ya. I don't know whether
Ya,
it's
Pak.
gonna work or not, but share computer sound. Okay, let's optimize share. Okay, you still hear my voice?
Ya, Pak.
Okay,
Yes.
so this is the oil system in your car. It sucks in from the oil pan. Ini oil pan tuh yang kamu buka buat buang oli, lalu tuang dari atas kan. Disedot sama oil pump. Lalu it goes through the filter. This oil pump is driven by the engine. This is the oil filter. Makanya oil filter itu harus selalu penuh ya. Kalau kalian ganti oli sendiri, make sure the oil filter is filled with, the new oil filter is filled with oil before you put it in. Kalau nggak, nanti ada beberapa detik engine kamu running without oil. If your oil filter is dry when you put it in. Jadi kalau ganti oil filter, diisi sedikit ya, oil filter. Nah, this oil goes into your journal bearings. Okay, it sprays up into the cylinders, but what is most crucial also are these bearings. Okay. Jadi journal bearingsnya itu diisi, dipressurize, actually it's pressurized. And so the shaft actually floats on liquid, on oil. Now you understand why the oil is very, very crucial, right? Changing your oil. If your engine runs even a minute or 2 minutes without oil, forget it, it's trash. It also lubricates the cylinder walls. Cukup smooth nggak sih animationnya di kalian?
Macet-macet
Aku banget,
Pak, di sini,
Pak.
Pak.
Burem semua, Pak.
Patah kayak stop motion.
Ya, ya. Ya nanti saya kasih linknya, kamu bisa ini. Tapi animationnya cukup simple lah, masih kelihatan kan?
Animation kelihatan, Pak.
Ya.
Tulisannya doang.
Okay, so now there is one more video. Okay, I want you to play this video. It's a bit longer than 9 minutes. Ini tentang hydrodynamic bearings ya. Let me put it in the chat. Okay, I send it in the chat. It's about 9 minutes long. Go ahead and watch it. Okay, engine bearing. So you see your crankshaft is like this, and each one of these shiny surface is covered with this setengah lingkaran ya bearingnya ya. Okay, it actually clamps onto these journals. These holes are for the lubrication to come in. The oil pressure comes in there, and the shaft is actually supported, just like the video you watch. Okay, so here's another assembly, right, of the rods yang naik turun. Ini crankshaftnya dipegang sama bearingnya ini. Jadi bearingnya itu is just a setengah lingkaran plate gitu, plain bearing, tapi inside there is oil. Okay. So I think that should be enough for today's session on plain bearings. Next, we're gonna start to get into gears, belts, and chain. power transmissions. But first, we'll talk about transmissions. Any question on plain bearings?
Pak, sorry Pak, ada post test nggak kita hari ini?
Enggak, kita nggak ada post test. Kita masih